We are the Arboreous Project. Due to the rapid advancement of launch vehicles in recent years, the demand for innovation within astronautics has never been higher. In this vein, the Arboreous Project set out to investigate the effects of mass optimization and its feasibility within launch vehicles. Mass optimization is the process of removing non-essential material from a part while maintaining its strength.
This project sought to optimize load-bearing structures in rockets to reduce a vehicle's overall dry mass and to reduce the cost of launching objects to space. For our senior design capstone project, we implemented mass optimization to high-powered rockets. This was primarily executed using analytical software that optimized a structure's given mass-to-weight ratio. The softwares used were Autodesk Fusion 360, ANSYS, and SolidWorks. These processes were applied throughout the entire vehicle and then brought to life using additive manufacturing to create our launch vehicle, AMOB 3.
The avionics section typically bisects the rocket, separating both the main and drogue chute, allowing for a segmented release. This makes the avionics section the most important part of the dual deployment recovery system, as it retains the shock cord, holds any necessary electronics, and the ejection charge for the main chute. Our case is a little different, as instead of bisecting our rocket and deploying from each end, we're going to have a singular deployment at the top near the nose cone for which our drogue and main would both deploy. And our main parachute will stay furled thanks to our electronic chute tie that will release at a predisposed altitude. The design started as a simple body tube with a thick bulkhead, but after being run through the topology optimization software in SolidWorks, the design changed drastically. The unique geometry is a result of test conditions set on the part, such as mounts for equipment, shock cord retention, as well as the material properties and load conditions. The results reduced the final weight by 60%, and further testing showed that it can withstand static loads of up to 10.3 kilonewtons in compression. This proved that the object was way over-designed and it would easily be able to withstand the final flight.
The body tube is the section that takes up the most volume on the rocket. It is the structure that runs from the top of the thrust structure to the avionics bay. Usually, in high-powered rockets, the body tube is a fully monocoque structure made from cardboard, fiberglass, or carbon fiber. In our case, we elected to make a semi-monocoque structure made from 3D printed ABS and wrapped in PVC to act as the aerodynamic skin. This resulted in a 3D printed, mass-optimized part that was able to withstand loads of up to 3 kilonewtons.
The objective of the thrust structure was to transfer the load from the motor into the upper sections of the vehicle. Our initial design was a simple cylinder with internal geometry that was used to mount the motor. Through mass optimization, we were able to understand the load paths that would be seen and redesign it. The new design of the thrust structure allowed the loads to efficiently transfer into the upper sections of the vehicle while drastically reducing the mass. The new contours of the motor allowed us to efficiently transfer the load while drastically reducing the mass. Results from testing showed that it could withstand up to 25.8 kilonewtons, or even 5,300 pound force.
The best part about our entire project is not really what we were able to do with it, but what the possibilities are. Our project was mainly a design exercise to learn more about mass optimization techniques, how to apply them, and how to fabricate these structures. Thanks to some of the recent advancements in 3D printing technologies, we were actually able to design and fabricate some of these structures for our model rocket case. However, thanks to larger and more complicated metal and composite 3D printers, it may be possible to create some of these structures for larger orbital vehicles. Thanks to these new and advanced 3D printers, it may be possible to redesign existing components on orbital vehicles and reduce their mass. Some of these structures include primary or secondary structures, nozzle or injector supports, or much more. Essentially, these parts would be redesigned using mass optimization techniques to improve the overall mass fraction of the vehicle and reduce the price per kilogram to space.